Welcome to McTox Curriculum, brought to you in collaboration with Western University, the University of British Columbia, and McMaster University. This presentation is part of McTox Curriculum built for residents and fellows from PGY 1 to 5. In today's module, we'll be learning about inhaled toxins. Today's module will allow you to recognize the classification of inhaled toxins and to explain the mechanism of toxicity for each group. We will also be discussing common examples of these inhaled toxins. Let's start with classifications. Inhaled toxins are classified into one of three groups: simple asphyxiants, pulmonary irritants, or molecular asphyxiants. As you know, the air around us does not contain only oxygen. It has a combination of nitrogen, 21% oxygen, and remaining gases that are present in smaller quantities, including carbon dioxide, helium, and argon gas. Toxicity from simple asphyxiants is caused by a gas that can displace oxygen in the ambient air. This displacement lowers the inspired oxygen concentration, FiO2, and causes hypoxia and hypoxemia. Examples of simple asphyxiants include methane, ethane, propane, nitrogen, helium, and neon. The treatment for these cases is to remove the patient from the scene and to supply supplemental oxygen. Our second class is pulmonary irritants. These exert their toxicity by dissolving in the mucous membrane of the respiratory tract and producing either an acid, an alkali, or a free radical. This triggers the inflammatory response. Signs and symptoms depend on the site of action, whether the upper or lower respiratory tract is involved. Irritants are further subclassified into another three categories based on their water solubility, which reflects how fast they will work. For example, highly water-soluble gases act immediately and cause injury to the upper airway. Examples of these are hydrochloric acid and ammonia gas. On the other hand, gases that have poor water solubility have a chance to make their way into the lower airways before exerting their effects. Now let's look at this in a clinical scenario. You have a 46-year-old gentleman who comes to your emerge after being found down at a petroleum refinery. Rescuers had to use respirators due to a first responder collapse during their first rescue attempt. You find out that the first responder was taken to a local clinic as he started to wake up and improve once he was away from the scene. However, your patient is still intubated and ventilated, although clinically stable. What do you think happened to the patient? To answer this question, think about the patient's location and environment, what happened to the initial first responder, and why subsequent rescuers were not affected. Before moving on to molecular asphyxiants, we need to do a quick review of the importance of the Krebs cycle in aerobic metabolism. The electron transport chain, which is located on the inner membrane of the mitochondria, along with other important enzymes, allows oxidative phosphorylation to occur and produces a large energy supply of a net 36 ATPs per cycle. Molecular asphyxiants are a group of toxins that work by inhibiting oxidative phosphorylation by blocking the electron transport chain in the mitochondria. When this happens, cells are forced to convert to the more inefficient anaerobic metabolism. This results in the production of excess heat and lactic acid for a fewer net total of ATPs. Many toxins affect the ETC and ATP production at the cellular level and share a common pathway. However, they don't all have the same clinical features. Time to onset, severity, and duration of signs and symptoms vary from one toxin to another. In addition, the ability to dissociate from the ETC, whether spontaneously or aided by a specific antidote, all depends on the toxin's own characteristics, which include its chemical structure and the exact site of binding. Back to the case and its toxicology analysis. Let's look at what we know. The patient was in a petroleum refinery, which indicates both an occupational hazard and industrial exposure, something that we don't usually see. This exposure also probably involves a much higher concentration of the toxin, which led to a profound effect. We also know that the initial rescuer was affected, which means that the toxin is in the ambient environment and has a rapid onset of action. His condition improved by just removing him from the scene, which reflects that the toxin has spontaneous and fast dissociation. Other rescuers were not affected because they used respirators, which proves that this is an inhalational exposure. So in summary, what we have is an inhaled toxin that causes rapid knockdown, spontaneous recovery, and is found in a refinery. According to the information provided, this patient must have been exposed to hydrogen sulfide. It's also known as knockdown gas due to its very rapid onset of action. Hydrogen sulfide gas is colorless and smells like rotten eggs. It dissociates spontaneously from the ETC and mitochondria once removed from the scene and supplemental oxygen is provided. In a massive or prolonged exposure, it may lead to cardiovascular collapse and respiratory arrest, most likely secondary to a prolonged anoxic injury. Other common examples of molecular asphyxiants include carbon monoxide, cyanide, and arsenic. Cyanide toxicity will be covered in the advanced modules in the theme of cutting-edge antidotes. Now, try and answer these questions, which will be taken up in your group discussion. 1. Are there any antidotes available for hydrogen sulfide exposure? 2. What are the clinical features of intermediate pulmonary irritant toxicity? And 3. List 5 symptoms of carbon monoxide toxicity. Thanks for watching, everyone.